Okay, so this is lesson 5 in moles and stoichiometry, and actually this is a really short lesson. We're just going to review how we deal with polyatomic ions when balancing equations, and I've kind of gone over this. And we're going to add something new. We're going to learn how to recognize what type of reaction is taking place when looking at the balanced equation. Now, we're only going to talk about 4 specifically types of reactions today, but there are many more. I may add one more, and then as we go through later units, we'll be adding a couple of different types of reactions. You should have out your reference tables when watching this video lesson because I am going to refer to Table J in the lesson. So remember, last time we met we were talking about balancing equations and we were dealing with polyatomic ions. So when balancing chemical equations, we said that polyatomic ions may be treated as a single unit rather than separate elements, as long as they stay together or intact during the reaction. So for example, SO4 stays as SO4 here, and OH stays as OH. So if they stay together, we can deal with them as a single unit. I know in a previous example, the SO4 stayed together and the OH didn't, so we had to deal with that separately. So in this equation, we have a polyatomic ions sulfate, which is your SO4, and hydroxide, which is your OH, and they both remain intact during the reaction. So we can think of this as 3 SO4 units and 1 SO4 unit, and 2 OH units and 3 OH units. So let's look at balancing this equation. Remember, our arrow is our equal sign. We have 2 ALs. We have 3 SO4 units, we have 1 Ca, and we have 2 OH units. And then on the right we have 1 Al, we have 3 OH units, 1 Ca, and 1 SO4. So I'm going to start with the SO4s just because I like them. So I have 3 sulfates on the left and 1 on the right, so I'm going to put a 3 here. That changes my SO4s to 3, but it also changes my CAs to 3. So now I'm going to go find my CAs, and I'm going to put a 3 here, which changes my CA to 3, but it changes my OH units 3 times 2. So now I have 6 OH units, which is going to change my OH here because I only have 3. But I know I can multiply that by 2. 2 times 3 is 6. So now my OHs are good, but it changes my ALs to 2, which is what I needed anyway over here. So everything now is balanced. So remember, if your SO4s or your polyatomic ions are the same on both sides of the equation, then deal with them as a single unit. So now let's look at what types of chemical reactions are taking place. In a single replacement reaction, you have one species replacing another. And how you can recognize it is you basically have an element, which is what you see here, plus a compound. So there's my element plus a compound. And that yields a new compound and an element. How I like to refer to this as something that you can understand is you might be dating somebody. So you either have a boyfriend or a girlfriend and a new hottie comes into town, and you usually don't break up with somebody to lower your standards, but you usually break up with somebody and get a new boyfriend or girlfriend to raise your standards. So that's kind of what's happening here. Your AuCl3 is a couple, and AG is the new hottie that moved into town. So what happened was CL dumped AU, gold, for silver, because silver had, I don't know, more goal-oriented, better looking, captain of the quarterback, or head cheerleader, whatever you want to think of it as. Now, in chemistry, obviously, elements aren't boyfriends and girlfriends. However, we can use table J. And table J is what's called a reactivity series. So just as you would choose a mate based on their characteristics and, you know, that they're motivated and goal-oriented and going somewhere with their life, table J is a reactivity series. So what happens is you have this compound, and the element that's trying to be pushing in has to be more reactive than the element it's pushing out. So if we look at table J, we can see that silver is above gold on table J, meaning it's more reactive, because it goes from most reactive to least reactive in table J. So AG basically pushes gold out, and gold gets kicked to the curb. And that's the same thing that happened here. Okay, chromium is above hydrogen on table J. It's more reactive, so it pushes hydrogen to the curb. And chromium is more reactive than Fe, so Fe gets kicked to the curb. So what this will look like, if we're just using letters as variables, it will be A plus BC yields AC plus B. So what you have to remember here, A, so A is more reactive than B. So the reaction takes place. Now, if A were less reactive than B, then the reaction would not take place. Because remember, in order to push another element out, you have to be more reactive. So sometimes you'll get a reaction and it'll say, will this reaction take place? So you're going to look at table J and see where the elements are. So that's the first one, single replacement. Double replacement is you have two compounds they switch partners and form two new compounds. This sounds like some Jerry Springer stuff if you ask me. Anyway, so you've got two compounds or two couples. Your your lead is hooked up with your nitrate, your sodium's hooked up with your chlorine. Remember that when we write compounds, we always have a positive and a negative, a positive and a negative. So what happens is the positive now hooks up with the negative. So Pb hooks up with Cl, and then your other positive, your Na, hooks up with your NO3. So that's all that happens. So if we look at this in variables, we have AB plus CD. Now remember, this is positive, this is negative, this is positive, this is negative. So they're going to switch partners. So A hooks up with D and C hooks up with B. That's a double replacement reaction. In our next type, we have synthesis, a reaction where we take more than one reactant and create one product. So this is kind of like marriage. Okay? Two unite into 1. So A plus B yields AB. The way you can recognize it is there is always one product. That's a good way to recognize synthesis. So here you have aluminum and oxygen forming aluminum oxide. Here you have hydrogen and oxygen forming water. Decomposition is like divorce. You have one splitting into two or more, depending on what you're starting with. But usually it's just two. Okay, so that's going to look like the opposite of synthesis. So you've got AB splitting into A plus B. So here we have barium carbonate splitting into barium oxide and carbon dioxide. Here we have hydrogen peroxide splitting into water and oxygen gas. And here we have bismuth hydroxide splitting into bismuth oxide and water. A special type of reaction that I would like to mention at this time is something called combustion. This is going to come up in another unit. When something combusts, we need oxygen as a component. And it's always going to produce carbon dioxide and water. This first reactant can change. So this is usually some organic compound. And a lot of time it's specifically what's called a hydrocarbon. The word hydrocarbon is exactly like it sounds. It's made up of hydrogen and carbon, thus the name hydrocarbon. So for example, this might be C3H8, which is something that you're actually all familiar with. It's propane gas, the stuff you put in your barbecue. And when I have that in the presence of oxygen, it can combust and turn into carbon dioxide and water. Now, of course, we need a balanced equation here. So let's see if we can balance this. I've got 3 carbons, so I need 3 carbons. And I have 8 hydrogens, so I need 8. So that gives me 3 times 2 is 6 oxygens, and 4 oxygens is 10. So that would be a balanced combustion reaction. So anytime you see oxygen yielding CO2 and water with some other compound, it's a special type of reaction called combustion. And I just wanted to introduce that to you now in case any of them come up in the practice set. And in the practice set, you're going to continue learning and practicing balanced equations, but now you're also going to tell me what type of reaction it is. Okay, that's it for this lesson.